Welcome, students! Today, we embark on a journey into the art of continuous motion. This lesson is the heart of senior year mathematics, where we move beyond static points to understand how things change and connect. We'll explore how continuity keeps a phenomenon occurring without any breaks, like a guiding thread, while differentiality acts as a mathematical microscope. It allows us to measure instantaneous speed and see the local shape of any trajectory. Let's start with a quick refresh of our basic building blocks. The domain, which is the set of all real numbers that have an image. The image itself, the unique value associated with each input. And the curve, the beautiful set of points that represent our function visually. Let's dive in.
Before we continue, dear friends, don't forget to subscribe, like, share the video with your friends, and also leave comments to encourage us to continue making this kind of content. Let's start with your intuition. Imagine you are drawing a path. If you can draw the entire curve from start to finish without ever lifting your pen, that is continuity. Look at the first box. Perfectly connected. This is what a smooth, continuous path looks like. However, mathematics requires us to be more precise. In the second box, we see a removable singularity. It looks like a tiny hole in the road, often caused by a 0 divided by 0 indeterminate form. The path is almost there, but one point is missing. Finally, the third box shows a discontinuity, or a jump. Here, the left limit does not meet the right limit at the same height. Your pen would have to jump to continue, so it's not continuous. Simple enough, right? Now, let's get rigorous and look at the formal definition. For a function to be continuous at a specific point A, there must be what I like to call a perfect encounter. Three things must happen. First, the value f of a must actually exist. Second, as x approaches a from both sides, the limit must exist and be a finite number. Third, and most importantly, that limit must exactly equal the value f of a. If the left and right limits are different, the function presents a jump. We also talk about continuity on intervals. For an open interval, the function must be continuous at every single point inside. For a closed interval from a to b, we check every point inside, plus right continuity at a and left continuity at b to make sure the endpoints are perfectly connected to the rest of the curve. Let's look at some examples to make this real. Most of our common functions are continuous on their entire domain of definition. Polynomials, like x squared or x cubed, linear functions, exponential functions, and natural logarithms are all continuous where they are defined. Even the square root function is continuous for all x greater than or equal to 0. But look at the floor function on the right. This function is a great example of a jump discontinuity. At x equals 1, the limit from the left is 0, but the actual value and the limit from the right are 1. Since 0 does not equal 1, the overall limit does not exist. There is a jump of 1 unit, so the function is not continuous at that point. Great observation. Before we continue, dear friends, don't forget to subscribe, like, share the video with your friends, and also leave comments to encourage us to continue making this kind of content. This is a powerhouse theorem you'll use often, the Intermediate Value Theorem, or IVT. Think of it like crossing the river. If you have a continuous bridge, the function, starting at bank f of a and ending at bank f of b, you must cross every single water level k in between at least once. Formally, if f is continuous on a closed interval, then for any real number k between the start and end values, there exists at least one value c in that interval where f of c equals k. And here is a golden nugget. If the function is also strictly monotonic, always increasing or always decreasing, then that solution C is unique. This is known as the Bijection Theorem, and it's your best friend for proving an equation has exactly one solution.
Welcome to the microscope effect. While continuity tells us a line has no breaks, differentiability tells us how fast things are changing at a specific moment. Imagine zooming in infinitely on a differentiable curve. As you zoom in, first 10 times, then 100 times, the curve loses its curvature and starts to look like a perfect straight line. That line is called the tangent. To calculate this, we look at the rate of change. Between a point A and a nearby point A plus h, the average variation is the change in the function values divided by the step size h. This formula, tau of h equals f of a plus h minus f of a, all over h, is the gateway to calculus. Let's define the derivative and the tangent line formally. Analytically, we say a function is differentiable at a if its rate of change has a finite limit as h approaches 0. This limit is denoted as f prime of a. Geometrically, this value represents the slope or gradient of the tangent line at that point. If you know this slope, you can write the equation of the tangent line. Y equals f prime of a times the quantity x minus a plus f of a. Look at the graph. As m slides along the curve toward a, meaning h goes to 0, the secant line between them pivots and perfectly aligns with the tangent at a. It's a beautiful transformation. Every master needs a toolbox. Here are the fundamental differentiation rules you should know by heart. On the left, we have common derivatives. X derives to 1, x squared to 2x, x cubed to 3x squared, 1 over x to negative 1 over x squared, and the square root of x to 1 over 2 times the root of x. Exponential e to the x is special because it stays e to the x, and ln of x becomes 1 over x. On the right are the operational rules for combining them: the sum rule, the product rule, the quotient rule, and the powerful chain rule for composite functions. Practice these until they feel like second nature, and you'll be able to differentiate anything. Before we continue, dear friends, don't forget to subscribe, like, share the video with your friends, and also leave comments to encourage us to continue making this kind of content. This is a very important conceptual point. The regularity theorem tells us that every function that is differentiable at a point is automatically continuous there. Think about it. If you can calculate an instantaneous speed, it means your movement didn't involve any teleportation or jumps. Look at the Venn diagram. The set of differentiable functions is contained within the larger set of continuous functions. However, beware, the converse is strictly false. A function can be continuous, drawn in a single stroke, without being differentiable. Sharp turns, corner points, or perfectly vertical slopes are blind spots where the derivative calculation fails. Continuity is necessary for differentiability, but it's not enough on its own. Let's look at a classic corner point example, the absolute value function. F of x equals the absolute value of x. Is it continuous at 0? Yes. As x approaches 0, the value approaches 0, which is exactly f of 0. No breaks here. But is it differentiable? Let's check the rate of change. From the right, the slope is 1. From the left, the slope is negative 1. Since 1 does not equal -1, there is no unique limit. This creates a sharp V shape on the graph, where a single tangent line is impossible. This proves our point. It's perfectly continuous, but it's not differentiable at that sharp corner. Keep this example in mind.
Your turn. Practice exercise. Problem statement. Consider the polynomial equation p of x equals x to the fifth minus 5x plus 1 equals 0. Questions. 1. Study the variations of the function p on the interval 0, 1. 2. Using the Intermediate Value Theorem, IVT, demonstrate that the equation p of x equals 0 has a unique solution alpha on the interval 0, 1. Take a few minutes to write down your calculations on paper.
Fantastic effort on that exercise. Let's walk through the correction together. For question 1, we look at variations. Since p is a polynomial, it's differentiable everywhere. The derivative p prime of x is 5x to the fourth minus 5, which factors into 5 times the quantity x to the fourth minus 1. On the interval between 0 and 1, x to the fourth is always less than 1, so the derivative is negative. This means p is strictly decreasing. For question 2, we apply the IVT corollary. P is continuous and strictly decreasing on the interval. P of 0 is 1, and P of 1 is -3. Since 0 lies between those two values, the Bijection Theorem guarantees that a unique solution alpha exists where P of alpha equals 0. Perfect. Exercise. The local microscope. Piecewise functions. Let f be the function defined on R by f of x equals x squared over x minus 1 for x greater than 2, f of x equals 3x minus 2 for x less than or equal to 2. 1. Show that f is continuous at x equals 2. 2. Study the differentiability of f at x equals 2. 3. Give a geometric interpretation of the results. Before we continue, dear friends, don't forget to subscribe, like, share the video with your friends, and also leave comments to encourage us to continue making this kind of content. Before we dive into the math of the piecewise function, let's look at our analysis and strategy. This problem is all about the perfect connection. We need to check if the two pieces of the function meet up smoothly at the border where x equals 2. To do this, we'll mobilize 3 concepts. 1. Left and right limits at the boundary. 2. The rate of variation, the difference quotient. 3. Geometric tangents and half tangents. Our strategy is simple. First, verify continuity by checking if the limits from both sides equal f of 2. Second, check differentiability by calculating the limit of the rate of variation from both directions. Third, compare the slopes. If the slopes match, we have a smooth tangent. If they don't, we have an angular point. It's like being a construction engineer checking if two pieces of a bridge align perfectly.
Let's solve question 1, proving continuity at x equals 2. First, we find the exact value of the function. Since the second expression includes x less than or equal to 2, we plug 2 into 3x minus 2 to get f of 2 equals 4. Next, the left limit, approaching from below. Using the linear model 3x minus 2, the limit as x goes to 2 minus is also 4. Now the right limit, approaching from above. We use the rational model x squared over x minus 1. Plugging in 2 gives 2 squared over 2 minus 1, which is 4 over 1, or 4. Amazing! Since the left limit, the right limit, and the actual value all equal 4, the function f is perfectly continuous at x equals 2. The bridge is connected. Now let's see if the slope is just as smooth.
Now for question 2, studying differentiability at x equals 2. We need to check the left and right derivatives separately. For the left derivative, we use the linear part. The limit of f of x minus f of 2 divided by x minus 2 simplifies to the limit of 3x minus 6 divided by x minus 2, which is exactly 3. So f prime left of 2 equals 3. For the right derivative, we use the rational part. The algebra is a bit trickier here, but after finding a common denominator and simplifying, we get the limit of x minus 2 divided by x minus 1. Plugging in x equals 2 gives 0 divided by 1, which is 0. So f prime right of 2 equals 0. Look at that. 3 is definitely not equal to 0. Therefore, the function is not differentiable at x equals 2. It's connected, but there's a problem with the slope. Let's see what that looks like on a graph.
Here's the visual payoff for question 3. The graph shows our function with a clear angular point at a, 2, 4. From the left, we have a steep red half tangent with a slope of m equals 3. From the right, the curve flattens out into a horizontal half tangent with a slope of m equals 0. Because these two directions are different, the curve has a sharp point. There's no unique speed or direction exactly at x equals 2. This is a classic exam trap. Continuity does not imply differentiation. Think of it like a continuous road that suddenly has a sharp, dangerous corner. You can drive across it without a gap, but you have to jerk the steering wheel suddenly. Understanding this distinction is a huge milestone in your math education. Keep that sharp corner image in your mind.
We've reached the end of our journey. Let's wrap up with a summary of essential ideas. Remember, 1. Continuity means uninterrupted motion. It's the key to using the IVT and finding roots. 2. Differentiability measures instantaneous speed and allows us to plot tangents and study the direction of variation. 3. The link. Every differentiable function is continuous, but watch out for corner points and vertical tangents where the reverse fails. 4. Exam advice. Always write down your hypotheses clearly. State continuity, differentiability, and signs before you invoke a theorem. As you've seen, the study of functions is no longer static. It is truly the art of mastering motion. You've done incredible work today. Keep practicing, keep questioning, and keep moving forward. You're a math champion.